Hi everyone. So how exciting that we're in chapter 9. Can you believe it? The year is winding down and today we're going to be talking about the tangents to circles, okay? So you've already learned what a tangent line is. So I'm going to actually draw a tangent. So a line that touches, actually let me do this. Let me use my segment symbol. A segment or line that touches a circle in exactly one place. So it can't go through the circle. It can only touch it on the outside of the circle. And there's a really interesting theorem that we're going to talk about called the radius to tangent theorem. Now, we are going to prove it, and we're going to talk about that a little bit now. But the radius to tangent theorem says that if you have a circle, so I have a dot in the middle and I call this circle M, and I draw a radius to that tangent and it meets at the point of tangency, okay, that it actually is perpendicular, creates a 90-degree angle. So if a radius is drawn to a tangent, it's perpendicular at the point of tangency. All right, so that's really nice because now what you might be thinking to yourselves, wow, if I connect it to any point on the tangent line, I've created a right triangle, which then helps us. Now, I also want to point out to you that part of that right triangle, so this part right here, is actually the radius, the same as it's another radius. So those are actually equal. All right, so let's talk about how we could use this. So the radius to tangent theorem. So if I tell you that if OT equals 6 and JO equals 10, find JT. And I have to tell you, though, that JT is a tangent to circle O. All right, so immediately if I see that it's a tangent to a radius, I'm going to draw in a right angle. I'm going to mark my diagram with what I'm given, which is OT 6, JO, so this whole thing is 10, and I'm trying to find JT. So this is a great place for our friend to help us. Who's our friend? Pythagoras. So we can use the Pythagorean theorem. So x squared plus 6 squared equals 10 squared. Now, many of you might be saying, Coach Fred, you don't need to do that. It's a Pythagorean triple. And you would be right. It is a 6, 8, 10 Pythagorean triple. So x actually works out to be 8. But again, remember with those triples, that will always work. Now, the interesting thing about that is, if I asked you to find this segment right here, this length, no, it's not to scale, but just remember that this radius is 6 because this is 6, and that's the radius. So then this segment right here would have to be 4. All right, so we could also throw some trig in here now that we've finished trig. And if I give you a segment and I tell you that line AB is tangent to the circle at point B, find the radius of the circle. So that means I'm going to be trying to find x. Well, the first thing I'm going to do is I'm going to mark my diagram with my right angle, and I look at this, I've given angle 55, and to that I have the opposite and the adjacent, so I'm going to use tangent. So tangent 55 equals 9 over x. Now remember, we cross multiply, always putting the x in front of the tangent because tangent is a function. We can't multiply x to a function like that. And then divide by tan 55 on both sides. And once we put that into our calculator, x would be 6.3. Okay? All right, so that's how we use the radius to tangent theorem. All right, now we got to talk about the clown hat corollary. Now, it's not really actually called the clown hat corollary, but from that idea of tangent lines, we have this theorem or this corollary, the thing that relates to it, if I draw two tangents from the same point. So if I pick this point and I draw two of them, to the circle, to the same circle, these segments, those tangents, are actually congruent to each other. So that's actually an important corollary coming from the radius to tangent theorem. So if two tangents are drawn to the same circle from the same point, then they are congruent. All right, so in this case right here, if I look at example A, I can see these tangents come from the same point, S, and they are tangent to the circle right here. So then these two segments are equal. So 2x plus 3 equals 25. Subtract 3 using that great algebra. So 2x equals 22, and x equals 11. All right, you try B. And I'm going to move on, okay, because now I'd like to talk to you about internal and external tangents. We can have two common internal tangents, which means they hit the circle. And actually, let me use the segment symbol again. So an internal tangent actually goes through in between the two of them. So now you might notice, let me fix this one a little bit because it kind of goes through like a secant. Something like this. Those are actually internal tangents, meaning they cross in between them. You'll see that they create an X. Now what you have to be really careful is because look how small they are. This segment right here and this segment right here, they're coming from the same point, so they're equal. And the same thing here, but it's really kind of tiny. So when you have those two common internal tangents, it can be hard sometimes to see that it is the clown hat corollary. External tangents are also very cool. External tangents are tangent to both circles, but they don't actually cross until maybe they get on the so on the outside. They wouldn't cross on the inside of the circles, so more like that. There we go. It's a little better. So those are called external tangents. All right, and we're going to be talking about those today a little bit, and we're going to try looking at this. This right here is a common external tangent. You can see that it's tangent to both circles, line CG. So if I draw the radius in right here, and here's my radius right here, you might notice that what I have created are some triangles. I connected A through the radius of B all the way to the tangent line at G. Now, because I have the radius drawn to the points of tangency, I know that I have right angles. So I'd like you to consider why triangle GBD is similar to triangle GAC. So why is this small triangle similar to the large triangle? Good review. All right, hopefully you're seeing that they have a reflexive angle. So they would be similar because of angle, okay? Which means that the sides are in proportion, which allows us to use the triangle proportionality theorem from chapter 7. The triangle proportionality theorem. All right, so this is where we're going to end up stopping today trying one of these problems. So here I have, ooh, look, same picture, a common external tangent. So I connect my radiuses, and I actually draw a line through both radiuses, and I know that the triangles are similar, okay? I'm going to put in my right angle just to help myself remember that. And then I can see that BD is 12. They told me this little segment here was 12. DG was 16. And AG, the whole thing was 30. And they want us to find AB, so this right here. And let me change colors so it's a different color. They want me to find X. They want us to find AC, so Y. And they want us to find CD, so we'll call that R, okay? All right, so I look at this and I see this triangle here is similar to the entire triangle. So I decide that I'm going to find y first. Okay, so I'm going to write a proportion that would be 12 over y equals, oh, I can't do that. Okay, sorry, I can't do that first. Can I? No, I can't. Let me back up. Let me back up and erase. So I see I have a right triangle right here, so I actually would use the Pythagorean theorem to find BG. That would help me first. So I see that right angle, and it's 12 and 16. So it appears to be a 3, 4, 5 triangle. So 3 times 4 is 12. 4 times 4 is 16. So 5 times 4 would have to give me 20, which tells me that BG would be 20, which then makes X 10. All right, now I have enough to use the triangle proportionality. So I can say 12 over y equals 20 over 30. So I can simplify the 2 and the 3, the zeros, and you can cross multiply, or you can use similar ratios. But I'm going to cross multiply, so I get 2y equals 36, and so y equals 18. Okay, so y equals 18. All right, so now I'm going to use the triangle proportionality theorem again, but this time I'm going to use the side splitter theorem, which is a corollary to the triangle proportionality theorem. The side splitter theorem says that if these lines are parallel, it divides the sides proportionally. So I can do 20 over 10 equals 16 over r. Now I am going to simplify. That becomes 2 to 1. So 2r equals 16. Divide by 2. R equals 8. All right, guys, so that's a little bit about circles. I highly recommend that you read the pages in your textbook, section 7.2, to help. But these are just some good basic examples of what you can do with tangent lines and radiuses drawn to them. And we're going to be doing some more investigation into it when we get to class. Have a great night.